Hi everyone, welcome to week 5, term 3. This week we're going to start a focus module. Up till now we've just done application modules that apply engineering principles to different applications, for example braking systems, and we did the introductory engineering fundamentals, and then we had a look at lawnmowers with engineering products. They're called application modules, but this one that we're doing now is called Biomedical Engineering, and that's a focus module which focuses on one area of engineering. Next year we do 2 focus modules. One's aeronautical engineering and the other one is telecommunications engineering. I hope that you've printed off the module notes that are on the Moodle site, and these are the slides that relate to that. But I'll put these slides up on the Moodle site so that you can copy these if you need to. So let's get started. This is what we're going to do in the biomedical engineering profession. We're going to have a look at the nature and the range of work of biomedical engineers. And the range of work is the scope of the profession. Have a look at a few current projects and innovations, health and safety matters related to biomedical engineering. Have a look at training for the profession, what you've got to do to become qualified in this area. Career prospects, whether you're likely to get a job easy or not. Relations with the community, how biomedical engineering professions relate with the community. We'll have a look at technologies unique to the profession, ethics and engineering. We'll have a look at the institution of engineers, ethics as regards to engineering, and we'll have a look at the role of engineers as managers. With the historical background to biomedical engineering, we'll be having a look at a brief history of the development of biomedical engineering over time. Have a look at the historical developments of products and the effects of biomedical engineering on society. So they're the areas that we're going to have a look at. Let's first of all have a look at the historical background to biomedical engineering, and this is all on those notes that I've given you, so it might be about a year to get those and have those beside you so that you can annotate. And have a look at the front page, page 31. You've got a checklist there that you can tick when you've revised that particular area. Very keen. Sorry, that's the wrong slide. For some reason, this puts the slides in the wrong order when I put it onto Blackboard. But so let's have a look at this: the nature and scope of the biomedical engineering profession. Remember, nature is what it involves, and scope is the range of work. The biomedical engineers, they apply engineering techniques and analyses, and analysis is to work out calculations and determine conclusions regarding medicine and biomedical sciences, and it bridges the gap between technology, medicine and biology. It's a fairly relatively recent profession. It started around about the early 1950s, 60s. So biomedical engineers generally work as a team, like all engineers. Very rarely an engineer works in isolation, and they apply engineering principles to the field of medicine. which is quite new as far as engineering is concerned. And biomedical engineers, the senior biomedical engineers, are generally the ones that are team leaders, and they organise professions under them, whether they be other biomedical engineers or tradespeople, technicians, and workers who have on-the-job training, for example, cleaners and people that they might be stenographers that get on-the-job training. This is the scope of the biomedical engineering profession down here. I've listed these scope of these areas are involved in biology, medicine, and engineering. And these are a few of them. Biomaterials. This is creating structures and materials to replace biological function. For example, they're developing a synthetic skin to replace skin for burn victims. What's another example? Fred Hires with cataract surgery. I don't know whether you've heard of Fred Hires, but he's he's dead now, unfortunately. But he was renewing the sight of lots of poor people in Africa by inserting a new acrylic lens in their eye, because the cataract was growing over their lens, and they were going blind, and so he replaced the lens, and he set up his own lens factory in Africa and made these little acrylic lenses. It's interesting that he's using, or they use acrylic lens now, which is polymethyl methacrylate. Or they've always used that, because in the Second World War, when the Spitfire pilots were flying and shrapnel hit their canopy, which is made of acrylic, they had acrylic splinters in their eyes, and when the doctors were taking the acrylic splinters out, some of it was so fine that they really couldn't get to it, and they were really amazed that the eye didn't reject acrylic. And so that's what they make the lenses out of now, acrylic, because the eye, as far as they know, that they guarantee these lenses for 120 years, because the eye doesn't reject acrylic for some reason. Biomechanics. This is applying the principles of mechanics that you are learning to understand the function of movement and cell and organ systems, so that they can replace those with synthetic biomechanical devices such as prostheses and organ transplants. Biosignals. This is the development of software and technology to monitor areas of the body, such as the brain, which is the EEG, the heart, which is ECG, I don't know what that means, heart, ECG, I don't know, you'll have to look that up. And also things like magnetic resonance imaging, the sorts of, and also ultrasonics. They're the sorts of biosignals that we're talking about. Biocomputing, developing of computer software to run all of these things here. For example, with bionic arms, you need software to run those sorts of things. And rehabilitation engineering, developing or using engineering mechanics and materials to design rehabilitation devices such as wheelchairs and walking frames and crutches and so forth. I've got to get this in order. Right, that's the right order. Let's have a look at current projects and innovations. There's many of these going on. There's thousands of them going on. But these are a few of them. Assessing knee joint stress in osteoarthritis. They're using strain gauges to work that out. Evaluating the performance of total joint replacement. That's an ongoing thing. You know that when they were using a particular sort of material that had a lot of cobalt in the metal, the cobalt was leaching into the bloodstream and poisoning the patient. And so they're basically going over to titanium alloys now, because titanium is biocompatible. Developing a bionic eye device, that's still in the process of being done. Don't forget that the example that I gave with the development of the lens for the eye, this is an ongoing thing too. They're gradually developing better shapes, and I know that they've got a multifocal lens now that they're using. Developing tools to predict and control epileptic seizures, and development of synthetic materials that can regenerate lost or diseased bone and cartilage, and as well as skin. I don't know whether you have done this yet, but there's a new health and safety regulation. It used to be called occupational health and safety, but now it's called work health and safety. And this was changed in 2011. And the idea is to get this integrated throughout all the states of Australia, so that every state's work health and safety will be consistent with the other states. And they've changed the word employer to a PCBU, which is a person conducting a business or undertaking. They did that so that everyone in the workplace would be covered, even people that are visiting the workplace. The aim of biomedical engineering is to improve people's quality of life, and this is not always the case, because you know as well as I do that you do get some faulty biomedical devices, for example, that hip prosthesis I was telling you about that had cobalt leaching into the bloodstream. And we've all seen the problems with cheap Asian breast implants that leak or poison the patient. Biomedical engineers are required by law to extensively test all new biomedical systems. There's laws set up in Australia that prohibit them from introducing them to the general public until stringent testing has been done. And that's the case in most countries in the world. Pardon me. Let's just have a look at the qualifications. This is the Australian Qualifications Framework, and this provides a hierarchy of educational qualifications in Australia. Now, some of you may not know about this, but let's have a look at the top level, which is level 10, is a doctorate degree. And a doctorate degree can take quite a long time. You generally have to do, for a genuine doctorate degree, you have to do original work, and it has to be approved by 3 universities before the person starts his doctorate thesis. And a person that has a doctorate is entitled to be called doctor, and he or she is the only one that's entitled to be called a doctor. You see people advertising doctor of chiropractics and even medical practitioners that have just got a bachelor's degree. They're not entitled to call themselves doctors. We see dentists now, which has got a bachelor of dentistry. They call themselves doctors. And vets, doctors. And the only people that are qualified to be referred to as doctor is a person that has done a genuine doctorate degree. And doctorate degrees, you can't do them by coursework. Genuine doctorate degrees, in my opinion, you can't do them by coursework. I know some fellows call themselves doctors, and they've got a doctorate as a result of coursework without an original thesis, and I call that they're dilute doctorates. A real doctorate is a person that has done a thesis on something that's never been done before. Okay, the next level is a master's degree. These and higher honours bachelor's degree. These three areas, the people generally go into research work. A bachelor's degree at university, the Bachelor of Engineering, entitles the person who has a Bachelor of Engineering degree to conduct a professional business, and he can be registered as a professional. Advanced diplomas, this is called a paraprofessional. You can't be registered as a professional. You can still do the same work that an engineer does, but you're not able to be registered as a professional, so that you won't be able to open up a business as a professional engineer. Same with a diploma, that's a paraprofessional. And then we go down to the TAFE courses. Diploma and advanced diploma can be done at TAFE. The certificate 4 is generally a trade course with specialised work skills. Certificate 3, you're gradually getting down to lower levels of qualification, and certificate 1 is just general on the job training, basically. So they're the qualification areas, or the hierarchy in Australia. Next slide. Training for the profession. This is tertiary training, this is university training, this is a bachelor's degree, master's degree, or a doctorate. Medical degrees take 4 to 5 years, and as you know, you've got to get a very high ATAR because of great demand for people getting into medicine. Engineering degrees generally related to biomedical, mechanical, electrical and chemical, and now more it's getting to have software included in that, software engineering, and these are 4 years duration. Depending on if you do a sandwich course, you'd have to check with the individual universities. You can do science or technology degrees in biology and biomechanics. These are 3 years. And specific biomedical engineering degrees and combined degrees, you can do those at some of the universities now, because biomedical engineering is a rapidly expanding area. Graduate diploma in biomedical engineering is available from some universities. That after you've got a degree, you can do a graduate diploma, and you've got to have this bachelor's degree in either science, engineering or medical science. Career prospects, biotechnology is an extremely large and rapidly growing industry in Australia. So there's a wide range of employment opportunities for graduates in these areas. For example, work in hospitals, servicing and optimizing equipment, medical device manufacturing, and nanotechnology and biotechnology. Nanotechnology means it's the technology associated with working with at the atomic scale. Graduates are employed as regulators in government organisations or as researchers for government, universities or private companies. These are the graduates in biotechnology and bioengineering areas. And work is also available in private medical and pathology laboratories, as you know. Next one, relationships with the community. I think you must agree that if a person is going blind and they do a simple operation, but a very highly technical operation with high-tech tools and machines developed by biomedical engineers, that person would be extremely grateful for biomedical technology to replace the sight or renew the sight in that eye. So generally biomedical engineers and technologists are well received by the community. Negative things, the failures are really magnified, like everything in the media. Negatives are magnified more than the positives, unfortunately. Religious communities may think it's playing God. Lots of people in different religious communities, they don't allow, for example, blood transfusions. And animal liberations, they really don't like testing drugs and medical equipment on animals, even though it's highly regulated. Some communities may oppose genetic engineering as it's thought to be unnatural by many people. So really, the positives outweigh the negatives, because the positives enhance people's lives and increase their longevity. Let's get to the next slide. Is technologies unique to the profession. Biomedical engineering is a relatively new and ever-developing area that progresses as discoveries are made in medicine, materials, and computing. And in aeronautical, for example, Teflon was developed by NASA for a space shot in the early 70s, and now Teflon is used quite a lot in biomedical engineering. Once a technology is developed for one area, many people work to apply it to other areas, which is the case with biomedical engineering. These are some of the areas: microengineering and nanotechnology. You know yourself that they can fit pacemakers into the body, and they can have drug administering cells in your body, and these are related to microengineering. So microengineering involves the design of very small devices that can fit into parts of the body, such as heart valves, blood vessels. Microengineering also involves the development of small cameras, such as endoscopes, that can provide visual inspection of almost all areas of the body. And you only need a very small incision now, because you can put an endoscope camera into the incision and have a look around to see where the damage is. Nanotechnology manipulates matter in an atomic and molecular level, and that's what nanotechnology is. It's used for DNA, cellular engineering, and regenerating biological tissue. Laser technology, they use laser technology for bloodless scalpels, so that the laser not only cuts it, but it cauterizes. In other words, it heat seals the body tissue so that it doesn't bleed. It's also used extensively in eye surgery to correct vision. You all know about laser technology. Awesome technology that my daughter had laser. She had to wear glasses from when she was 17, and when she took them off, she could not see in the distance. It was all blurry. She had laser technology when she was, I think, around about 30, and she's 12, 13 years old. Now she's had the laser technology, and her eyesight is perfect without glasses. And so you can just imagine how she feels about biomedical engineering. Growth of artificial skin. This is related to cell biology, and Australia is in the forefront of that. There's a doctor in Western Australia that has developed the technology for the regeneration of skin for burn victims, and she won a Nobel Award for that. X-ray and digital imaging, this enables the determination of problems without having invasive surgery, and this is a major area of biomedical engineering. Ethics in engineering, I've listed 4 areas here. That is the code of ethics for the institution of engineers. And biomedical engineers have a legal, and it's based on laws passed by Parliament, and an ethical responsibility. And this is what we've got here, based on moral principles. And that's what ethics means, based on moral principles, to ensure that their projects do not harm people or the environment. These are the 4 areas that I'd really like you to remember. Demonstrate integrity. You've got to act on the basis of well-informed conscience, so that your conscience is clear with all the decisions that you make. You've got to be honest and trustworthy, and you've got to respect the dignity and the advice of other people. Practice competently. You've got to maintain your skills and knowledge by doing courses. Respect areas of competence objectively, so that you don't allocate a job to a person that is not competent in that area. And you've got to be aware that if you aren't competent in that area, you can't give advice. You've got to direct the person to a person that is competent in that area. Exercise leadership, because engineering is leading of other areas or working collaboratively with other people. You've got to uphold the reputation and trustworthiness of the practice of engineering. Support and encourage diversity, so that engineers get skills in a lot of areas that are related to their profession, and communicate honestly and effectively, taking into account the reliance of others on engineering expertise. So you've got to be able to communicate with other people in your team, so that they can tell you things that you don't know, and you can tell them things and direct them as part of a team. Promote sustainability. This is to do with the environment. That's a fact, so I won't worry about it. You've got to engage responsibly with the community and other stakeholders, so that if you're doing, say, a bypass, and it involves a community of residents along the road, you've got to notify them and keep them up to date with what's going on. You've got to make sure that you practice engineering to the betterment of the community, and that's why engineering is such an important area, profession in today's society. Engineers are working all the time to enhance our quality of life, and no other area of profession works as diligently as engineers to enhance our quality of life. I know medical practitioners do and surgeons do, but they can't work without a biomedical engineer developing the tools and equipment to do the outstanding work that they do. And you've got to balance the needs of the present with the needs of future generations, so that you've got to make sure that you don't use resources inefficiently, so that it will create hardships for future generations. Next slide is slide number 9. Engineers as managers. Make sure you know the definition of management. A very simple definition is management is the efficient use of resources to achieve predetermined goals. And these are the different resources. So biomedical engineers as managers, most, and I'll put all in brackets here because I think virtually all biomedical engineering developments have been the result of teamwork and the management of resources. For each project, engineers must manage cost, quality, ethics, impacts on society and the environment, market, the marketplace trends and demographics, so that their developments are conducive to the development of all these areas. Sorry about that. We'll just keep going. I'm running out of time. Management is an integral part of engineering. I'll just stop this for a moment, and I'll just pull. Sorry about that. It's all happening. So it's important for you to understand that engineers have to be good managers, because management is an integral part of engineering, and because an engineer has to work collaboratively with others, and generally the engineer, because he's a highly qualified professional, he is generally the leader of a team. Next slide. We go up. Number 10. Let's go through the historical background of biomedical engineering. Remember, these are all on your module notes, so that you can annotate this as we're going through. In the 17th century, the relationship between mechanics and biology began to flourish. Before the 17th century, everything was just done ad hoc, and with scientists such as Galileo, Borelli and Boyle, Hooke, from Hooke's law frame, started to apply their knowledge of physics and mathematics and biology to the human body, to understand how cells regenerate, how blood flows, and how your limbs work in a biomechanical way. 20th century, the 1900s, saw a necessary interaction between engineers, physicians and scientists to develop the tools so that surgeons can operate. So in the 60s, it became clear that medical advances depended on engineering problem solving, demonstrated in 1962 by the development of hip replacement implants. 1962 is quite early, and that's they weren't using titanium then. They were using a high-strength nickel cobalt steel. Alloy steels were originally used for implants, like I just said, but have subsequently been replaced by more biocompatible metals such as titanium alloys. Friction surfaces were made from polymers but tended to wear and are now being replaced by wear-resistant ceramic-based materials. I'll show you these when I see you later on this term. Development of polymers and composites have been enabled the manufacturers of products such as heart valves, artificial hearts, prostheses such as the carbon fibre blade foot. 21st century, many universities have incorporated biomedical engineering in their faculties because of the great demand and how appropriate it is in today's societies. And future developments, they're going to have surgery via joystick, so that the surgeon will be watching a monitor to do the operation remotely using optical fibre, so that a surgeon can be in Sydney and operating on a person at Broken Hill via this optical fibre link. So we've got optical fibre technology. They use optical fibre because it has huge data carrying capacity. It's just as fast as the impulses along a copper conductor, because remember, light travels at the same speed that electromagnetic radiation travels through a copper conductor. But the advantage of optical fibre over a copper conductor is the tremendous, because it's such a high frequency, is a tremendous data carrying capacity. The higher the frequency, the more data, because every time the wave goes up and down, you've got a bit that can be transmitted. And so if it goes very quickly, like light can go up to terahertz, even picohertz frequency. And so optical fibre has tremendous data carrying capacity, whereas copper conductor doesn't have the same data carrying capacity, but it goes as quick because it travels at the speed of light. Nanotechnology is a developing area. Genetic engineering, where you can develop products such as meat from genetics. You don't have to grow it on a cow. You can develop yourself from muscle tissue now. Miniaturization, cell tissue research, glues in place of sutures, composite materials like the carbon fibre blade foot, and much more. Prior to the 1900s, why is that not? I should have done this before, but let's do it now. Historical development of products prior to 1900. The medicine had little to offer the individual because there wasn't that sort of technological development. You had mummification and crude crutches, and wooden prostheses were used, like the pirates used to use wooden prostheses. And a 2000 BC mummy was unearthed with a prosthetic big toe. They used to use wood prosthetics in those days. 1816, invention of the stethoscope. Early 1900s, we had X-rays, electrocardiogram. Oh, that's what ECG means, electrocardiogram. And 1927, respirator with the eye and lung for people to aid their breathing. Electroencephalogram, EEG, that's what it means. I thought it was that, but I didn't think they I thought they broke up the words to get that acronym. But anyway, that's 1929, the EEG. Electron microscope was around 1930, and that enabled us to view dislocations in metals as well. Heart-lung machine developed in 1935, allowing the heart to be stopped during surgery. Remember, this one helps in breathing, but this one allows the blood to be circulated, and you can stop the heart during the surgery. 1950s to the present, and pacemaker in 55. Computers in the late 50s began to be used in medicine, very important for medicine, computers. The space race started a lot of developments, like as I said before, Teflon materials, and development of different techniques so that humans can live in space. 1962, the first hip replacement, which we mentioned before. 1969, significant cochlear, an Australian ear implant, and you can see that that's a very wealthy company now. 1988, laser cataract surgery and intravascular stents. This is what I was talking about, laser cataract surgery. Not necessarily laser, cataract surgery is also the insertion of an acrylic lens in the eye. They do a very small cut up the top of the eye, and they suck out the lens and leave the lens envelope there, and then they fold up an acrylic lens and put it in the insert, and it springs open in the envelope of the lens. And so you've got a multifocal acrylic lens, which will give you excellent sight. The World Wide Web in 1989, very important for doctors and biomedical engineers to communicate with other people and send their designs internationally. 2001, telesurgery, so that a doctor in Sydney can operate on someone in, as I said, Broken Hill, remotely using optical fibre, and the bionic eye is being developed. And finally, we've got the effects of biomedical engineering on society. The benefits to society, you can see a lot of the benefits here. It allows people to regain functions, increases longevity. Biomedical contributes, usually biomedical engineering contributions usually result in happier people. Healthier, more active people results in less financial drain on the community. Provides innovative technology for use in other areas of society. And biomedical engineering is now a large industry providing employment for many people. Costs, there are also always risks associated with all procedures, and some may not go well. Some cultures don't like it, and some research involves the use of animals, and even though stringent constraints are placed on this, some people still don't like it. Okay, so I hope you understand all that, and you can answer the CWR this week on all of this. Thanks for listening. I'll speak to you later. Bye.